All right, now we're finally getting started. I know you're excited to continue this. Last time we left off with a brief intro preview of what we were going to be doing, and that is going to be looking at a word problem today. Now, what we're doing here is we're looking at statistics, but I really want to take this opportunity to show you how to use Desmos as a great tool for you to answer this type of a question, which asks us about the linear regression. Oops. Let's get back zoomed in there. So as usual, make sure you have pen and paper handy. Ideally, it would be the same document that you're using on the previous. So we're going to have a linear regression equation. And what that is a line. And it's a line equation that fits data, because data can be scattered and might not follow a perfect pattern, because there's variation along the way, but there will usually be some kind of general trend that is observed, and the line that we use to describe the trend is one that almost perfectly fits the data, basically as perfectly as we can get it. We don't have our expectations too high, but we're trying to find a line equation that will go through most of the points ideally, or it would just sort of minimize the gap. It'll minimize the error, so that it's pretty much like an approximating line, also called sometimes a line of best fit, right? You get the idea, is that I can draw this several different ways, and sometimes it goes exactly through the data, sometimes it doesn't. Well, to do this by hand is really tedious, and it's quite unnecessary. If you were a statistics major, you would need to know these kinds of things. You would learn them and do them by hand at first, and then later you would find out how to do them with technology. But you would always have the equations sort of memorized. And the lines that I'm drawing might not necessarily be perfectly linear either. So let's just get a sample one. Let's say that represents the data, and we can see that there's a positive slope. And so it tells us a story. It tells us a feature of the data. It tells us that as maybe time goes on, some value that we're measuring is increasing, right? That's the big picture of a linear regression equation. So let's look at the situation here. The median price, you don't need to actually calculate the median here. The median is just a metric that is used in statistics. It takes into account all of the different values of something, and it lines them up in order from least to greatest and takes whatever's in the middle. So in this case, if we get all of the existing single-family homes, we can take all of those values of single-family homes, line them up in order from least to greatest, and if we have any repeats that are the exact same price, that's okay. We have to list them multiple times, one for each home, and then we would take the middle value. That has been recorded, and it's noted that it has increased consistently during the past few years. However, the data in this table that we're going to use show that there have been some differences in various parts of the country. So we have the South category and we have the West category. And you'll notice, first of all, that in the same year, 1999, the median price already began differently, right? This one is larger in the West. It's larger by, if you want to go percentage-wise, you could go percentage-wise, but the difference in price here is about $28,200. Oops, sorry, 27,000. Whoa, yeah, $27,800. So that's the difference in the price. And then if we look later on, when the values of both types of homes have gone up, the difference in price is now almost 100,000. In fact, it's 90. What's that? $92,800. So the difference, the gap, is increasing. That kind of suggests, right off the bat, that kind of suggests that the value in the West is increasing by more than in the South. Because if it were increasing by the same amount, if they both were increasing by the same amount, we'd have the same gap in between them. So that's something worth noting. Another small thing worth noting is, that there is an observed increase each time. So this is sort of like plus 2K. This is like plus 7K, almost 7.5K. This next one is plus 8K, exactly 8,000. And then finally we have plus 5,000. So even though the increase is kind of a lot in these 2 years, 2001 and 2002, the increase goes down a little bit. It's still increasing, but it's just not increasing by as much when we get to 2003. Okay, that's just an interesting little fact to observe. Now let's look at this, which is going up by, well, pretty much 23,000 almost. That went up by a lot. Let's see. Now the next one is going up by about 17,000. Okay, so it's not going up by quite as much. And then we're going up by 25,000 basically. So it's going up quite a lot in 2002 for both categories. Maybe there was something that happened in 2002 that caused all the home values to go up or something. Like across the country, whether you're in the South or the West, it's possible they had some similar factors that went into the increases or decreases. And then lastly, we go up by about 22,000. So yes, the increases are much more significant when we're looking at the houses in the West. The median houses, which is a decent reflection of all of the houses, a decent reflection. Depends on what kind of houses are being built. Is there just like a buttload more houses being built and they're all going up in value, or are there more high value single family homes that are being built, like maybe more luxurious single family homes that are being built in the West? These kinds of things factor into the equation. Now, the real process, this is all to give you context, so I hope that you're not just like tuning all this stuff out. It does kind of matter so that we can interpret what is happening to these values, like what's happening to the price of a single family home. It's going up in both cases, but my point was that it's not going up the same. And so the question is asking us for the linear regression in the South, but then part C is asking us for the linear regression for homes in the West. So we're going to do each of these linear regressions. I'll show you how to do that right now. Let's go to Desmos. So in Desmos, I'll eliminate that. Pretend you have a blank slate. You should know Desmos by now. It's a great website. Free, beautiful math. You can click this plus and add a table. And now we have X values and Y values. What I want to do in the X values is I want to indicate the year somehow. And instead of putting 1999 as the year, I'm just going to type 0, which sort of represents like my first year. Then we have 1, which represents the year 2000, 2001, 2002, 2003, and those are our data points. You could also use 1, 2, 3, 4, 5 if you wanted to. It doesn't really matter all that much. But the point is that I don't want to plug in 1999. It's kind of unnecessary to push everything in time out that far. We can simply say that the starting point is like our 0 point. That's a much more convenient way to do it. Okay, so let's plug in some of these values. First, we're interested in the South. So we're going to start with 145,900. In fact, if we want to represent this in thousands of years, we could just call this 145.9. Okay, and then in the year 2000, we have 148 on the dot. And then in 2001, we have 155.4 thousand. In 2002, so I'm just copying the data as Y values, that's the home value, 163.4. And lastly, we have 2003, which saw the median price of single family homes at 168.1 thousand. Okay, so there are some data points. We don't see the data points because they are way off the chart unless I were to go look way up here. So what we're going to do is we're going to click this little bottom corner zoom fit button. This does some stuff as well. Actually, you can add a regression. It already kind of anticipates that I'm going to need a regression, which is cool. We're going to zoom fit. So this is zooming things in. Sorry, my circle, my H circle is kind of in the way. It's going to frame this in a way that the data is visible very clearly. There wouldn't be this like circular bubble thing in the way for you. It frames the data and zooms into the appropriate area to try to capture all the data, but not, zoom out too far to where you're just getting a bunch of unnecessary space. Next, we're going to add a regression, and we're going to add a linear regression. They kind of already have it there for us, which is nice. I do want to show you how to also find the regression or calculate the regression by hand. This is what you would do. So if this were a custom regression, let's say that we didn't type all that stuff that it just typed for us. You would do y1. You're going to have to hold shift and the minus key. Hold shift and press the minus key, and that puts the little cursor down. See, if I put a 1 right here, oh, I guess it did kind of already do it for me. But you would want to have that subscript have a 1. And then we're going to use the squiggly, the famous squiggly. So it's kind of by your numbers. It should be on the left, right underneath like the escape button. Shift and then the squiggly. Now we're going to have m, which we typically use for the slope. And then we're going to use x subscript 1. And that is going to, plus b. And that is going to call the x values from this list. And it's also going to call the y values from this list. And it's going to just sort of force a linear equation. Now, there's some complicated math that goes into it. Like I said, if you're a statistics major or something, you'll learn this in more detail. You don't really need to know this if you're not going to be a statistics major. But I just want you to understand that we're using this line to approximate the data, which is not perfectly linear, but it follows a general pattern, and we can sort of average it out or approximate it with this linear regression. And here we have the slope. These parameters are important. The slope is the m value. You know that. We talked about slope-intercept form before. And the b is the initial value. So that's kind of like the starting point. So even though the actual median price was 145.9 thousand, based on using this equation, this line, the line approximates it to be 144.2. Now, which one is true? Is one better than the other? Is this linear regression line wrong because it doesn't match that first bit of data? No, not necessarily. This is just where it had to pass through so that the line could pass by, get as close to all of the data. So any one particular point is not more important than getting close to all of them. See, this one happens to go through a point. That's kind of nice. That won't always happen, but in this case it does. All right, so that is the regression equation. We have 5.98x plus 144.2. Y equals 5.98x, and I think rounding it to 2 decimal places is like, that's plenty, plus 144.2. This is the linear regression for the homes, single-family homes in the South. And remember, this is in thousands. So these values are in thousands. So it's not simply going up by 5.98 every year. It's going up by 5.98 thousand every year, which is almost 6,000 every year. And that seems pretty much like an average, right? If we looked at this data that we calculated earlier, we look at these changes that we calculated, went up by 2,000 and then 7.5 thousand and then 8,000 and then 5,000. So I guess it's good enough to say that things went up by like 6-ish thousand per year. Okay, what does the slope represent? Well, the slope is the change in the y value over the change in the x. What do the y values represent? These represent the change in price of single-family home. I guess I should probably type all this stuff, right? Where are you guys cringing while I just write through this by hand? Let's get it right here. Price of change. Price of single-family home in thousands per year, because the change in the x is a change in years. Oh, I should say in the South, because we were just using data from prices of homes in the South. Now we'll do the exact same thing for the West. In fact, I would like you to try that out. I want you to do the same thing, create a regression. So go ahead and pause the video, see if you can create the regression using Desmos, and then resume when you're ready, or when you figure out you're pretty much on the right track, you can go ahead and continue the video, and maybe the video will catch up with where you're at, writing things down and such. Make sure you're putting in the data carefully. The calculator is a very powerful tool, but if you give it the wrong data, it's going to give you a false conclusion because you gave it the wrong data. It's crunching the wrong numbers if you don't plug in the correct numbers. Let's see. So we're going to change this. We're going to change these values. Let's get a different table in here. We're going to have 0, 1, 2, 3, 4. And we're going to start off somewhere different. Where are we starting off? Here. We're starting at 173.7K. And I'm choosing to use thousands. You could put 173,700 if you'd like. But as long as we just convert it into thousands, this works perfectly fine. Next is 213.6 thousand. Okay, next is going to be 238.5 thousand. And lastly, in 2003, the median price of single-family home is 260.9 thousand. Let's zoom it to fit. I see one point here, but I don't see all of them. So we zoom to fit, and we move it a little bit because of my H circle. And then we have that. Let's add a regression. Bam. And you notice there are different types of regressions. If I had a quadratic regression, that would do its best to make a parabola go through all the points, which obviously isn't going to work very well. Look at that. Such a huge parabola. It's like looking at a planetary orbit compared to, the size of a small state or something. So that looks almost linear, but you can see that it curves a little bit. So this quadratic function captures a lot of the data. It gets pretty close to capturing all the data. If we look at a cubic one, it's a little more smooth. It's a little bit better accurate representation. If we do quartic, then we really have the ability to get through quite a lot of these values. Exponential regression, it's going to be very, very slowly growing. Exponential regression. Logarithmic regression, that one's not really going to work, as you can see, especially because I think we can't plug in 0. Only work if the first column is all positive numbers. Right. So I'm kind of curious. Let's see what happens if I do this. If I index everything, move it over a little bit. So it can do a logarithmic regression, but as you can see, it's not really great fitting. So that's just showing you all of these different tools that we have. Let's see, this is going to be 0, 1, 2, 3, 4. And yeah, all of these different types of regression. We could even use a sine or cosine function. Look, this is a very interesting sign because this is just a small piece of the sine and cosine function. Wowza. Yeah, okay. Enough of that. So let's just go to the linear regression. I'm sure I've wasted enough of your time and you've written everything down already, right? So you have the linear regression written down, y equals mx plus b. And you'll notice that this slope is significantly larger than the other slope. The starting point doesn't really matter unless, your overall budget is a factor here. But if we're just talking about the increase in the values over time, the starting point doesn't really have doesn't play as much of a part. If we're just trying to track the change over time, we're not really caring where it started at necessarily. We just care about how much it changed each year. So it seems like the equation is 21.65. Let's see, y equals 21.65x. Again, that's in thousands. Plus 170, what was it? 173, was it? 173.32. Okay, and again, y is in thousands. So the question is, where's the median price increasing more rapidly? Increasing, which means slope is important, more rapidly. Now this question is very interesting because we could answer this in terms of percentage, or we could answer this in terms of overall slope. Typically, they're going to be concerned with overall slope. But for certain circumstances, like if you're really trying to analyze a market, maybe for investment purposes or something, the percentage of growth is probably what you should be more interested in. I don't care if I make $100,000 on something. I know that sounds crazy, but what if you had to spend $500,000 to do it? Well, that's not really as big of an increase then, because you spent $500,000 to get $100,000. Now, if I spent $1,000 and I made $40,000 profit. That's much less profit than $100,000. But guess what? It only took 1,000 to do it. So my percentage of increase is massive. The amount of growth that happened is massive, even though the overall number doesn't necessarily represent that. So typically what they mean here is they mean slope. But down here is like a side quest. I'm going to put that it could be a different result if we're talking about percentage. Right, so for example, 23,000 increase, that's a big deal from 173,000. In fact, that's pretty much like almost 1/7. That's basically around 14%. But then later on, when we go up by 25,000 from 213.6K, that's not quite as significant. In fact, that's like a 1/17th. So that's only like a kind of ballparking here, but that's kind of like a 6.5% increase. And so if you owned a home that was worth 173K and then it went up to 196.4K, you would increase the value of your home by 14%. Whereas if you bought a house in 2000, what is this, 2001? Yeah, if you bought a house in 2001 at 213.6K and it went up even more than it did in 1999 to 2000, you still wouldn't really have made as much per dollar for your investment. You would have only gone up by 6.5%. Now, overall, it's still 25K. It's still a great deal. Another example is when you go from 238.5 thousand to 260,000, we're only going up by 22K. And so that also is about a 6% increase. I mean, not even that. It's probably like a 5.7% increase, I believe. Oh no, it's almost 10%. So I must have had something a little bit off over here. Let's represent this properly because I want to use a calculator to make sure that I'm doing this correctly. Okay, so we start at 213,000. So 25 divided by 21. Oh, whoops. 25 divided by 213.6. Got it. That's 11.7%. I was really underselling that. 6.5%. That's way too low. Now when we go up 22,000, so 22 on 238.5, now that's not quite 10%. So this one is like 9.2%. So you can see that even though these are comparable amounts, in fact, this 23,000 is not that far off from 22,000, but by the time this value is already large, 22,000 doesn't do as much of a percentage. And so that's one way to look at it, in the real world when you're analyzing stuff for stock purposes or investment purposes or something. What they mean here in the equation, though, I think they just mean like which one is growing more per year. And so that would be in the West for sure. Yeah. Okay, so we tackled a word problem and we got a handle on how to write linear regressions in Desmos, which is a really useful skill here. Now, this is sort of a shorter video because we only discussed one word problem. But I just want you to have the wherewithal of what kind of numbers and what kind of operations you'll want to do when you're considering word problems. Okay, I'll see you guys next time when we talk about piecewise functions. If you haven't already checked out my video on absolute value as a piecewise function, you should check that out because that's what's coming up next. I will see you next time.